you. So I decided to pick a more recent paper of Morgan's to connect to because I don't have quite the long history in neural nets that many other people do. And I want to say this is work that I've been supported by several grad students, and this quarter I was teaching a class in continuous space language processing. So I'm pulling some results from leveraging it. You know, psychologists do experiments on their students. I have my students do experiments. So I'm pulling some results from that, and I'm in teaching this course, I spent a bit of time talking to Jeff Zweig, Li Deng, and Xiaodan He at Microsoft. So forgive the Microsoft influence on this presentation. Okay, so here we are. Have you had enough neural nets yet? No, of course not. Good, there's more to come. Yes, I bet there's some of you who are saying yes. Okay, I will end with something different, hence the term here, continuous space. Okay, so I'm going to start out talking about neural nets for language processing, which a lot of which is happening. I think I'm going to be a poster child for Dan Jarofsky's talk about the importance of cross-pollination. And so I'll talk about some common themes in that sense. So some people don't look back, other people don't look across, and that's what's, I think there's a lot that can be learned from looking across. And then I'll come to the deep versus wide question and end up in defense of shallow models. So Brian can give me a hard time. Neural nets have been used for language modeling. Early work started with language modeling. Apparently there was earlier work than I'm even aware of. So it started out with some work by Bengio and colleagues working on feed-forward models. It started to get big when Mikolov made his recurrent neural nets available to other people. The software's out there. Lots of people started using it. And so more people were doing language modeling with neural nets. And you know, in the last few years, it's really, last decade, I would say, it's really exploded. So there's some work that was done early on chunking, tagging, named entity recognition, doing a bunch of different tasks. There's work that was done at a lot of work that's happening at Stanford on parsing, sentiment analysis, a lot of work happening at Microsoft, speech understanding, recognizing interestingness, whatever that is, web search, phrase translation. There's a very large body of work right now on semantic similarity, which I'll spend a bit of time talking about because I'm pretty interested in that. There's new approaches now for, you know, just like Hervé was talking about, well, let's not just use the DNN for the observation distribution. Let's use it for everything. So there's now new approaches that are using it for everything. And this last 6 months, there's been this kind of fire of stuff happening on captioning images. And I should point out two of these three big papers that came out in arXiv because everybody wants to be there first. Two of the first authors worked with Morgan. So Hao Feng is one of my grad students. He did this at Microsoft and Oriel. So it's actually really cool stuff. All right, so one of the things that people are sort of excited about with neural networks is this whole concept of word embeddings. Let's think bottleneck, tandem, that sort of stuff. Basically, you take your word, it's a one-hot zeros and one indicator. You put it through a neural net. You do a transformation where they're all getting the same transformation. This was the original feed-forward network, and then put it into a hidden layer, and then you predict another word. And you can take this representation. Now we've got a continuous space representation that can represent a word. And the idea here is that now I've got this continuous space, I can look at distances. And if we have the binary thing, you know, purple and violet are two totally different words. But once we have a continuous space, we can look at similarities. Okay? And purple would not be the same as banana, right? But when we have continuous spaces, we can say those are far away, and purple and violet are not so far away, right? So that's kind of the idea. And so one way you can do it is with a standard neural net, but you can do it with any sort of neural net. So people have done this with RNNs, with multitask networks. They look at word context, word history, log bilinear models. All of those things are useful for finding these embeddings. So here's an example that I've shamelessly stole from my colleagues at Microsoft, who I shamelessly got to give a lecture in my course for me. Basically, they were illustrating the concept of learning embedding. So this is just to show you it actually works. It seems a little bizarre, but it actually works. So in this projection down to 2 dimensions, and when you project that low, things really get messed up. It's much better at higher dimensions. But anyway, here you see, if you expand these out, there's countries here, there's states here, there's months there, there's sports-related things there. So it actually really works. So there was this pretty influential paper back only about a year and a half ago, where they looked at taking RNN embeddings for representing words, and they said, okay, we're just going to do a vector space model, all right? So I'm going to try to solve an analogy problem. I've got, you know, kings is to king as queens is to what, right? And so what they said is we're going to just say, if I look at all the words in plurals, you know, I can think about all those differences as averaging them. That indicates plural, all right? That's a vector space representation. So they basically said, okay, I can take the vector of kings, subtract out plural, subtract out masculine, add in feminine, I should be able to get queen, right? And in fact, it actually worked better than a ton of other things that were out there. It blew people away. Now, why does this make sense? Okay, you saw from the illustration that it actually sort of works. But it turns out you can think about this as if you think about what this model is doing, and I'll show you a little tiny bit of math later on. Basically, people are looking at exponential models. So if you take log linear models. So if you take the log of an exponential model, what do? Is you get something linear, all right? If you go back to my original thing, I'm taking my one hot input and multiplying it by weight matrix. What does that do? It picks out a vector, all right? So what I'm doing when I take the log of that distribution is I'm getting a vector, okay? So if I do a log likelihood, that's subtracting 2 vectors, right? So that's roughly why it works. Now, if you really think about it, and you start thinking about it this way, you can also think of reasons why it doesn't work, but we won't go there right now. Another way that I will explain a little bit later, in language modeling, you can think about what you're doing is you're learning projections to a lower dimensional space that help you predict the next word, okay? And what this turns out to be is a sort of soft parameter tying between words. So you're learning similarities of words. You're learning, and those similarities, because you're predicting the next word in language modeling, are similarities in terms of both syntactic and semantic function. Okay? So the implication here is it provides a new way to learn word classes. So this has implications not just for language modeling, but also for learning features for text classification problems. Okay, so there's actually been pretty dramatic progress. So the groundbreaking paper a year and a half ago showed, all right, if I try to do this with latent semantic analysis, so I take big matrices, term document matrices, and do singular value decomposition, trying to solve those analogy problems, I'm getting 17% correct. This is all on the same training data. If I use RNNs, if I can increase the dimension, I can get up to 35% correct. And then the same guy did another paper a few months later with the new thing, which is the word2vec, which looks at skipgrams and continuous bag of words. And there, same dimension, he's doing it way better. One of the interesting things here, this is recurrent neural net is what people would call deep. These are shallow. Okay, so this was sort of late 2013. Now along comes 2014, and things keep getting better. This is a totally different task. So let's start with these guys here. So let's say this, which was doing really well here, is now a totally different task. This was just syntactic, all right? Now it's a syntactic analogies like the king-kings, queen-queens. Now it's also semantic analogies like Athens, Greece, Paris, France, sorts of things, okay? And this didn't work so well. But this one did. But if you start applying other techniques, well, things can get better, all right? This is a more shallow model. This is also a shallow model. But then, and this is another shallow model. This is GLOVE, which is log bilinear. And then there was some complaints that the people who did GLOVE didn't do fair comparison. So there's other stuff. So Goldberg published this little note on the web. And so you can see we're doing better. So we're still doing great. There's some differences. It's supposed to be the same data, and the results aren't matching. So I'm not quite sure why that is. But anyway, there's been a lot of progress. And all this is like in a year and a half. So neural nets, this continuous space method, it's having a huge impact. All right, so let's look at some common themes here. And this common themes, I'm now relating back to acoustic modeling because almost everybody here is an acoustic modeling person. So what are they learning over in the language processing world? They are learning that if you want to do unsupervised learning of feature transformations, neural nets work better than PCA. PCA in the language world is latent semantic analysis. Same thing. What a surprise. Whole word models kind of are a problem. We learned this back in speech recognition a long time ago. Many neural net architectures are being explored right now. The same thing is happening, as Steve pointed out, star NN. And so that's all over the acoustic world. Multiple streams help. Morgan would not be surprised at this. It's true for language, not just speech. And it's not just different analysis techniques. It's also, we know from speech, audio and video help. Well, video and language actually help. And multitask training, that helps. So it's as evidence that everything is the same. I decided that Steve's slide was actually perfect because everything he listed here, people in the language processing community are exploring separately. All right, so there's a lot of common things that people are exploring. There's also common problems that they're running into, not surprisingly. If you have limited training data, the results aren't so good. Hence, I asked my training data question. And domain differences cause challenges. So this is where I'm abusing my grad students in my class. I made them work on the analogy problem, and I said, do whatever you want. I don't care if you get bad results. I want you to just go try stuff, and let's see what happens. And they tried a bunch of different things, but since the Word2Vec is easy to download, a lot of people did that, but they tried all kinds of different data sets. And so you can see going through here, more data is better, but then there's another data set that I didn't include because it's slightly different configuration, but there's also this issue, so amount of data matters, but vocabulary coverage matters. So these guys, this had like only 50% vocabulary coverage. Go down here and you have 20, here's 20% and it gets up. So vocabulary coverage matters. If you don't have the word in your, you can't solve the analogy problem. But style matters. So one student said, aha, I'm going to cover the vocabulary. So he got this blog data that we had collected. Didn't work at all. Pretty bad results. It was worse than this with the like 30% out of vocabulary. So style matters, vocabulary coverage matters, all those things that you would expect to matter, of course, matter. But there's this temptation to use Google text because there's so much, and you can learn so much, and they work better when they cover your task. So we had the DARPA Bolt project has this translation program where you're talking about people out in the field interact, doing medical things and repairs, infrastructure, reconnaissance, whatever. And there's 7,000 words in that vocabulary, which is not huge, that are not covered by these Google Ngrams. So vocabulary is actually really important. Okay, so now we're on to deep versus wide, and I decided I really needed to, in thinking about this talk and thinking about, now that I'm finally, I resisted neural nets for so long that I have to listen to Morgan. So I went to this paper and I pulled out, first, what does he say in his abstract? Okay, because I don't want to read the whole paper. So, while the deep processing structures can provide improvements for this genre, whatever that genre was, choice of features and the structure with which they are incorporated, including layer width, can also be a significant factor. So we're going to want to think about that. And then the second thing, new approaches to learning, blah, blah, blah. Okay, this is going to have advances. However, despite such advances, it could be the case that we will not make further substantial progress until we better understand what limitations in our signal representation and models are causing the error. So part of my goal, where I'm heading towards in the rest of the talk, is trying to understand this stuff. Okay, so I'm going to question a few things inspired by Morgan, always pushing to questioning, not to mention Hervé. Anyway, so I'm first going to ask the question, well, what do you actually mean by wide? So, you can be wide by having more units, but as you pointed out, you can be wide by having more analysis methods. You could also be wide by having a shared, if you do multitask training, you can have a shared component and a task-specific component. You can also be wide, and this is something that's people eons ago looked at it in speech, and maybe they still are, or they've forgotten, but they are looking at, in language processing, having side information. So a vector that represents the context, a multi-sentence context, for example. All right? All right, so that's just, we need to think about that. I'm just raising questions. What do we consider computational costs? So one thing that was interesting to me by teaching this class and talking to people about things, I found out that, this whole Word2Vec thing that everybody's excited about. And so the guy who did the RNNs for language is now doing the shallow stuff because you could train on a whole lot more data for the amount of computation. And so this is a different way of looking at deep versus wide is thinking about if you have a limitation in computation resources, it might be better to have a shallow structure. The other thing I'm going to point out, that in that analogy task that I just went through, the best results are all with shallow models. Now, I'm going to avoid the negative term of wide and go with the perhaps equally negative term of shallow, but being an engineer, electrical engineer, I'm okay with being shallow. So that is what we're going to do. So there's a couple different shallow models that we can think of. The word-to-vec sort of things are shallow in that there's just one hidden layer. But you can have a shallow model by just using an exponential model, right? So you could have a log linear model, that's maxent. And you could have a log bilinear model, which is what I'll go into next. I should point out, most recently, one of my grad students who's really, really good and has just gotten fabulous results, very productive. We're trying to we did this experiment with neural nets, and he said, well, we got to do this baseline, you know. So he did this maximum entropy baseline, and really, you know, if you're going to do it right, you have to do regularization. Bummer, maximum entropy is winning now. So, you know, if you have to think about regular everything, you know. So, okay, he's still going to try to get the neural net to win, but anyway. Just do better regularization. So this is I should say this is with a low resource task. Okay, log bilinear models. So these were introduced. Well, there's a bunch of different variations. The key idea here, and I'll do it. You don't have to do this for language modeling. It can be for anything, but I'll just try to explain it in the language modeling sense. You have if you want to do X given history, you have the observation, a matrix, and the history. Okay? Let me just go through some equations and explain this. So this is our version. The low rank, we call this a low rank model. And it's a log bilinear model, and the variations are interesting and worth exploring, but let's look at the fundamental idea. So the maximum entropy model says I'm going to have a feature vector that's my x's and my observations and my history, okay? And then I'm going to have a weight vector, all right? So now I'm going to rewrite that and have the observations, a matrix, not a vector, a matrix, and then the history, all right? Now, if I take the log of that, I'm left with this bilinear function, right? Now, if I take that matrix and I do singular value decomposition, try to represent this in a low rank way, I can rewrite, so the singular value decomposition, I can rewrite this in terms of two transformations of the word space. So, and I can train this using standard log likelihood and gradient searches and all that. But the key thing that I'm doing here is I'm taking this big matrix, I'm reducing the rank, so I'm doing a lower rank approximation of that matrix. I rewrite these as two transformations, so I'm learning a low-dimensional continuous space embedding of words. And in this case, I have different representations for words in history. So in this case, I learned this decomposition from the big matrix. If I go back to some of these other things, this says, okay, both projections are the same. This is saying we're learning it from the big matrix. This is saying, well, they're different, but I'm going to learn them separately. So those are kind of the differences. But fundamentally, that's what's happening. So that's what, so remember, we're really starting with a big matrix. You can think of that. So if I move on to, if I reconstruct that big matrix, what I'm learning is similarities of the words. So these stripes are similarities of the words in terms of how they're used to predict words or to be predicted. All right? So that's what I mean by it being a soft clustering, soft parameter tying. Okay, now I am going to jump on a point that Hervé made about sparsity, but I have a bit of a different take. So the low rank stuff is important because there's similarities in language, and we want to reduce that. But also there's exceptions in language. So if I look at what the low rank is doing, it's screwing up on things like New York, because York is not new in the sense that a item of clothing is new. So it's just a different sort of thing. Kind of is another thing that it's something you say in conversational speech. It's not something that they go together in a different way. The low rank also overestimates really much because it says really is like very, but really, people don't say really much. They say very much, but they don't say really much. So the solution here is to add a sparse component. So we're going to represent our parameters in terms of sparse things and low rank things, because there's two things going on in language. This allows us to make better use of varying amounts of data. It's going to have the nice advantage of being convex. So the thing that's different here is that I'm saying that both the low rank and the sparse are important. They're complementary. They're getting at different things. So the low rank is getting at the similarity. It's getting at style. The sparse component is getting at topic things. It's getting at idiolect and sociolect. And I'll show this to you by saying we're going to write this. In fact, I'm going to use a factored model. This being not a deep neural net is actually easy to do. So I have a factored model where I'm going to say I'm going to have low rank components that depend on different factors, okay? This is Supreme Court oral arguments. So there's the general Supreme Court data. There is what people say in a case. That will be topic related. There's who's talking, and then whether you're a justice or a lawyer, okay? And so I can learn different low rank and sparse models for those different types of people. And what you find is you learn things in these, in the sparse, you actually, yeah? Oh, okay. So you learn things about the case. This is just the sparse stuff because it's easier to illustrate. That's the red stuff. You learn things about the fact that the general stuff, this is spontaneous speech. These are people who are, arguing as they go, so they're disfluent. You learn idiolect. Justice Breyer says all right all the time. And you learn things about the role. So justices say things like in your view. So we can learn a lot about language. If I try to play around with topic modeling, so you're using this factored representation. So I have a different matrix, sparse low-rank matrices for the different topics. So you can learn weights just like you learn weights in mixture models. You can also learn interesting things. The exceptions turn out to be very interesting. So if we look at the sorts of things that pop out as being unique in different topics, when you represent them in a way where you factored out the other stuff in language, you get much more interesting things. So in life partners, you get things like soulmate, problem solving, physical attraction, and here you get good things too. But on some, this is TF-IDF, which is actually better than other baselines we tried. So this was the best baseline of the things we tried. But for other topics, you get much more interesting things. So minimum wage, you get things like food stamps. So much more interesting data. So in summary, Neural nets are not just for audio and images. There are many applications in language processing, but they don't always have to be deep. I'd argue that shallow models are useful for training with lots of data because they're low cost. They are useful for training with limited data because they are easy to regularize. And they're useful for investigating structure and language because you can make them more interpretable. And with that, I will stop.